Hi everyone, I'm Jingoo Han. I'm a PhD candidate at Virginia Tech. So this talk is about Marble, a multi-GPU OO job scheduler for deep learning on HPC systems. This is the first work to schedule deep learning jobs based on non-linear scalability of multiple GPUs for the rated supercomputers. This is a collaboration with Virginia Tech, Rochester Institute of Technology, Ivan Research, and Oak Ridge National Lab. First, first, we'll start by looking at the ratage for computers. The ratage for computers try to equip multiple GPUs into their computer nodes. 4 years ago, only 2 out of the top 10 supercomputers are with GPUs. However, last year, 6 supercomputers have GPUs. There is another trend. These top 10 ranked supercomputers train deep learning models on these multiple GPUs for scientific research. For example, analyzing climate pattern, modeling the universe, classifying medical images, and predicting protein structure. I'll explain CNN. CNN is a kind of deep learning network. CNN is the most popular approach for image classification. It contains multiple convolution layers. Convolutional layers extract features from images. Pulling layers upsample the data to avoid overfitting issues. After repeating convolution process, learned features are classified by fully connected layers. Training CNN model involves multiple convolution operation with a large number of parameters. Through training, parameters are adjusted according to input images. The convolution process involves a huge number of the multiplication and addition operations, so it results in huge computational overheads. Also, increasing the number of the parameters leads to I/O overheads. Each CNN model needs different computing capacities and I/O workloads according to their model designs. For multi-GPU training in HPC systems, data parallel approach is widely used because scientific data is usually very large. Data parallel approach divides data set into multiple batches. Each GPU has the same model and performs training with different portion of image data set. It enables each GPU to have its own copy of the parameters. Whenever one iteration is finished, GPU 0 gathers the gradients from other GPUs. First, we checked scalability of multiple GPUs by measuring training throughput on the Summit supercomputer. However, we found that deep learning training is not scalable in multi-GPU HPC systems. Unlike previous studies, multiple GPUs cannot provide linear scalability. So we also measured GPU utilization and found that GPU resources are not fully utilized. High-end GPUs are very fast, and thus computation overhead is not a huge overhead compared to non-HPC systems. As a result, coordination overhead is higher than the achieved parallelism. Another reason is that conventional schedulers are unable to fully utilize multiple GPUs to their full potential. We also checked the limitation of HPC scheduler. Existing HPC scheduler has limitations. Job scheduling, queuing, and monitoring on HPC systems are maintained by batch schedulers. Jobs are usually placed into job queues and dispatched to computer nodes when required resources are available. These schedulers do not provide dynamic resource management. The resource configuration is defined by the users at the time of job submission, and it remains fixed until job completion, even if the resources are configured inefficiently and wastefully. These schedule targets long-running jobs because the majority of the resident application on HP systems are still modeling and simulations. These schedulers do not support features optimized for deep learning workloads and treat deep learning jobs as black boxes. Recently, several approaches are proposed for deep learning scheduling. It usually focuses on adjusting cluster configuration and GPU locality. For example, the number of parameter server nodes and worker nodes are configured dynamically, but it does not work well with HPC environment. These works target non-HPC systems and focus on more flexible cloud environments. Also, it does not consider nonlinear scalability of multiple GPUs. So we propose Marble. Marble is a deep learning scheduler that considers the nonlinear scalability of GPUs. Based on nonlinear scalability, it schedules an appropriate number of GPUs per node for GPU resource efficiency. We'll talk about Marble design. Marble consists of job scheduler and resource monitor. Resource monitor checks availability of GPU resource and deep learning job processes. Job scheduler assigns deep learning jobs according to the scalability of characteristic. Our design goal is to reduce overall job completion time by allocating the optimal GPUs according to non-linear scalability. The second goal is to increase GPU utilization by co-locating multiple jobs in parallel. So different training jobs are running simultaneously on the same computer node. In this way, Marble improve the GPU resource efficiency. Let's assume that there are 6 GPUs and 3 deep learning jobs are submitted. First, Marble assigns the first jobs based on its optimal GPU number. In the case of ResNet 50, the optimal number of GPU is 3, so 3 GPUs are allocated for the first job. After allocation, currently 3 GPUs remain. Then the second job is allocated to these 3 remaining GPUs. Scheduler checks the status of each job by monitoring GPUs. When the first job is finished, scheduling algorithm needs to choose the optimal number of GPUs for the ongoing second job. Then, when the first job is completed, the second job is suspended by using a checker pointing mechanism. After that, the second job is resumed with its optimal GPU number. In this case, the optimal number of insertion V3 is 4, so 4 GPUs allocated to the second job. After assigning 4 CPUs to the second job, currently 2 GPUs remain. So the third job is assigned to the other remaining 2 GPUs. We use the Summit supercomputer as our test bed. It has 6 V100 GPUs per node. Each V100 GPU has 5,120 CUDA cores and 16 gigabyte main memory with the memory bandwidth 900 gigabyte per sec. Power 9 CPUs and V100 GPUs are connected by NVLink 2.0. We also choose TensorFlow as our deep learning framework because it is one of the most popular framework for deep learning training. We also built TensorFlow from the source code to run on the IBM power-based system. We trained for different CNN models using ImageNet data set. ImageNet data set has 1,000,000 images of 1,000 categories. For single node training, 3 different job sets are selected. These jobs are chosen randomly. In the case of single node training, overall job completion time is reduced by up to 48%. This is because Marble scheduler choose the optimal number of GPUs for the fastest throughput. At the same time, GPU utilization is increased by up to 46%. This is because, unlike the existing approach, our Marble scheduler assigns multiple deep learning jobs on the same compute nodes. So in this way, it can increase the resource efficiency of GPUs. Next, we conducted experiments on multiple nodes using one parameter server and AIM worker nodes. Unlike the single node setting, the training time is very fast, so we choose another 3 different job sets for multi-node training. Like single node training, it also shows similar performance trends. Job completion time is also improved by up to 31%. GPU utilization is improved by up to 35%. We also compare the performance between our Marble and other deep learning schedulers such as Optimus. Instead of considering multi-GPU scalability, Optimus adjusts the number of workers and parameter servers. According to our measurement, job completion time improved by up to 47%. Now we presented a Marble, a multi-GPU scalability-oriented job scheduling system for fast deep learning training, which leverages the non-linear scalability characteristics of parallel training using multi-GPUs on the latest HPC platforms. The evaluation of Marble using thermal supercomputer and the representative workloads shows a performance improvement of up to 48% and an improvement in the GPU utilization by up to 86% compared to the default LSF job scheduler. So if you have any question, please contact me. Thank you.